In this video, we're going to continue our discussion of parsing with the idea of a derivation. So a derivation is a sequence of productions. So beginning with the start symbol, we can apply productions one at a time in sequence, and that produces a derivation. And a derivation can be drawn in a different way. Instead of as a linear sequence of replacements, we can draw it as a tree. So, for example, if I have a non-terminal x that appears in a derivation, then when I replace x, I can represent that by making the children of x the left-hand side of the rule that I use to replace x. So when I apply the production x goes to y1 to yn, I add the y1 to yn as children of x in the tree that I'm building up. Let's do an example. Here's our simple grammar of arithmetic expressions. And let's consider this particular string, id times id plus id. So what we're going to do now is we're going to parse this string, and we're going to show how to produce a derivation for the string and also at the same time build a tree. And here it is. Over here there is a derivation beginning at e and ending in the string that we're interested in with one production applied each step along the way. And here is the corresponding tree. And this is called a parse tree. This is a parse tree of this expression, or of this input string. So let's walk through this derivation in detail. On the right side in red, we're going to have the tree that we're building up, and on the left side in blue, we're going to have the steps in the derivation that we've taken so far. So initially, our derivation consists of just the start symbol e, and our tree consists of just the root, which is also the start symbol. So the first step is that we have a production e goes to e plus e, and what that means is over in the tree we take the root of the tree and we give it three children, e plus and e. So now we replace the first e by e times e. So we use the production e goes to e times e, and that means we take the first e in the tree and we give it the three children e times and e. Continuing along, we take the first e here that remains in this expression and we replace it by id, which means we make id a child of the leftmost e in the tree that we're building. And then we replace the second e by id using the production e goes to id, and finally we do the same thing with the third e, and now we have completed our parse tree. So here again, from the start symbol to the string we were interested in parsing, and in the process we built up this parse tree of the expression. Now there are a lot of interesting things to say about parse trees. So first of all, parse trees have terminals at the leaves and non-terminals at the interior nodes. And furthermore, an in-order traversal of the leaves is the original input. So let's back up and look at our example and confirm all of this. If we look at the leaves, we can see that they're all terminals. Okay, and the interior nodes are all non-terminals. In this case, since we only have one non-terminal in our language, all the interior nodes are e, and the leaves are the terminals of the string. And then we can see that if we do an in-order traversal of the leaves, we get exactly this input string that we started with. Furthermore, the parse tree shows the association of the operations, and the input string does not. So you may notice here that the way this parse tree is constructed, the times binds more tightly than the plus, because the times is a subtree of the tree containing plus. And so this means that we would do the e times e first before we would add e. And some of you may have wondered, well, how did I know to pick this parse tree? Because actually, if you think about it, there's another derivation. Actually, there are several derivations that will give me a different parse tree where the times is towards the root and the plus is nested inside the times. So let's not worry about that for right now, and let's just say that somehow we knew that this was the parse tree we wanted, and I gave you a derivation that produces that parse tree. Continuing on, the previous derivation I showed you is actually a very special derivation. It's what's called a leftmost derivation, where at each step we replace the leftmost non-terminal in our string of terminals and non-terminals. And there's a natural and equivalent notion of a rightmost derivation. And here it is. Here is a rightmost derivation for the same string. Again, beginning with the start symbol, ending with the string we're interested in. And notice that at each step, we're replacing the rightmost non-terminal. So here we replace the only non-terminal e, and we get e plus e. And then in the second step, we replace the second non-terminal e with id, and so on for the rest of the string. So let's just illustrate this entirely with our little picture here of the tree and the derivation simultaneously. So once again, over here is our tree, and this is the root, the start symbol e, and in blue is our derivation. So we begin by replacing e by e plus e. That's the only non-terminal, so it's the rightmost one. And then working from the right side of the tree, we replace the right e by id. And then the left-hand e gets replaced by e times e. And now the rightmost e that remains is replaced by id. And finally, the only e that remains and is also replaced by id. Now, I want to point out that the rightmost and leftmost derivations I showed you have exactly the same parse tree. And this is not an accident. Every parse tree has a rightmost and a leftmost derivation. It's just about the order in which the branches are added. So for example, if I have the first production, e goes to e plus e, now I have a choice on how to build my tree. I can either work on this subtree or I can work on that subtree. And if I build this one first, that will be a rightmost derivation, if I continue to always work on the rightmost non-terminal, of course. And if I work on this one first, I can use that to do a leftmost derivation. Now, it's important also to realize that there are many derivations besides rightmost and leftmost. I could choose non-terminals in some random order to do my replacements, but the rightmost and leftmost ones are the ones that we're most concerned with. So to summarize, we're not just interested in whether a string is in the language of a particular context-free grammar. We need to have a parse tree for that string. And a derivation defines a parse tree. But it turns out that one parse tree in general has many derivations. And in particular, we're interested in the leftmost and rightmost derivations. These are the two kinds of derivations that are important in parser implementations.